Hello, my dear students. Welcome again in this online class of statistical mechanics. As we have discussed in our previous two chapters, that is related with the classical statistics. Basically, the statistics or statistical mechanics, it is being divided into two main classes. First two units, they are related with the classical statistics, and third and fourth unit, that is related with the quantum statistics. Now, the classical statistics, which have been discussed in the first two chapter, and it is because it used utilized in those units, we use the classical results of MB statistics, or Maxwell Boltzmann velocity distribution of the particles. So classical statistics, it interpreted successfully many ordinary observed phenomena. So basically, what is the difference? So in this lecture, I will discuss about the difference between this classical statistics and quantum statistics, and how in this quantum statistic, that in unit number 3 and 4, what type of notations, operators, which we will discuss. Yeah. So, in classical statistics, many ordinary observed phenomena such as temperature, pressure, energy. So, it explained all those thermodynamic parameters, but it failed to account adequately the several other experimentally observed phenomena such as black body radiations, photoelectric effect, specific heat at low temperature, etc. So the failure of this classical statistics, it forced the to discuss the new quantum idea of discrete energy, of this exchange of energy between this system, and along with the, how it is being exchanged with this reservoir. So this new quantum statistics, it was investigated. The quantum statistics, it was first formulated in the year 1924. So by Bose. So he explained this quantum statistics using Planck's radiation law. So where he used purely statistical reasoning, so on the basis of certain fundamental assumptions, so which are different from classical statistics. So later on, Einstein in the year 1925, so it utilized practically the same principle which Bose used, and he evolved this kinetic theory of gases by substituting this classical ambient statistics with these new quantum techniques. So thus a new quantum statistics, it is known as Bose-Einstein statistics, so which we generally known as BE statistics. So it came to be accepted. So later on, in the early 1930s, Fermi and Dirac, they quite independently modified this Bose-Einstein statistics in certain gases on the basis of some additional principle. So what was this Pauli's suggestion? So he used this electronic structure in the atom, and he derived this Pauli's exclusion principle. So according to this principle, in any given orbit in an atom, there can be only one and only one electron, it being impossible for two electrons to coexist in the same quantum state. So in statistical mechanics, this exclusion principle, it takes the form that two or more phase point, it cannot possibly occupy the same phase space cell. So if I write here, so two or more phase point, so which we generally known as the representative points, cannot possible to occupy the same phase space here. So this lead to recognition of a second kind of quantum statistics, which is generally known as Fermi direct statistics. So thus quantum statistics, it can be put into two subclasses. So first one is Bose-Einstein statistics. So this is applicable to identical, indistinguishable particles having zero or integral spin. And these particles who follow this BE statistics, they are generally known as bosons. And the examples of these bosons are helium atom at low temperature, and photons. So second is FD statistics or Fermi direct statistics. So this is applicable to identical, indistinguishable particles which is having half integral spin, and these particles, they must obey this Pauli's exclusion principle, that is it is not possible for two electron or two particle to coexist in the same quantum state. And the examples of fermions are, so the particle which follow this FD statistics, they are generally known as fermions. And fermions are, we have discussed in nuclear physics in detail about these particles. So which are electrons, protons, neutrons, etc. Neutrino. So let us discuss with the help of some diagrams the illustration of this difference between these three statistics. So in classical statistics, so in classical, or I will write here the Maxwell-Boltzmann statistics. So if I have chosen two particles and two cells, so if I have two particles and they need to be occupied with the two cells, so what can be the maximum number of microstates which are possible? So in classical statistics, each particle which is generally recognized individually, so hence the particles, they are distinguishable. So in classical statistics, particles are distinguishable, and each particle, it is likely to be in one cell as in the other. So if I have two particles P and Q and having two cells, so there is chances that P will occupy the first cell and Q will occupy the second cell. So there is chances that they will change their position, and there is probability that both the particle, they can be present in one cell. So it can be in the first cell or it can be in the second cell. So this means that in the classical statistics, each or both of the particle, they can occupy any one of these two cells. So thus in this case we have four possible arrangements. So this is our MB case. So second is our BE statistics. So in this BE statistics, the particle, they lose their individuality. So because they are indistinguishable, so it is very difficult to distinguish them. So we must concentrate our attention on the cell rather than the individual particle. So therefore we cannot distinguish the particle. So we generally consider them as all are identical. So let us say it is P and Q, they can be considered as the same particle. So either X is in the so it is only having the one arrangement. So second arrangement is possible. So they can be present both in the first cell, and the third arrangement is they can be present in this second cell. So the possible there are three arrangements so which are possible for this BE statistics. So in the Fermi direct statistics, the particles are indistinguishable, and again we have to concentrate our attention on the cells rather than the individual particles. So second, in this FD statistics, so there is one more case we have to take into consideration, that is they obey Pauli's exclusion principle. So according to which it is not possible to have more than one representative point or particle in any one cell. So therefore only a possible arrangement for this FD statistics is one particle, it can be present in one cell. So therefore in FD statistics there is only one arrangement which is possible. So when there are a larger number of cells and comparatively fewer particles which we need to be arranged in them, so there is no great difference between these three statistics, because the probability of any cell which contain more than one particle, it is very small. So but in the case when the number of particles, they are very large compared to number of cells, so then these three statistics, they lead to different results. So this is the basic idea of these three type of statistics and the major difference between these three statistics. So let us discuss the basic concept of quantum mechanics. So we all know that it is experimental fact that light has a dual nature. So light has dual nature. So that is, it can act as a particle as well as a wave. So in some phenomena such as interference, diffraction, polarization, so light exhibits as the wave nature, while in some phenomena such as photoelectric effect, Compton effect, pair production phenomena, so where the emission and absorption of particle radiation, it is being happened, so in that cases it act as the particle nature. So in this connection, so with the dual nature of light, de Broglie thought that matter, the material particles, so it must have also the dual nature. So the particle nature of matter is well known, and it is very verified by this using the charge to mass ratio of material particles. So in the year 1923, Louis de Broglie, he proposed that moving particles, so I will write it here. So moving particles, whatever is the nature has wave properties associated to it. So if while the particle it is having some finite velocity or having some finite momentum, so then it is having some finite wave amplitude. So he gave the famous de Broglie hypothesis. So that is the wavelength of that wave, it is equal to h over p. So where p is considered as the momentum, so we generally write this equation as h over mv. So where m is the mass of the particle and v is the velocity of the particle. So this proposition of this de Broglie equation has been verified theoretically and experimentally, and many physicists so they tried to prove this equation by applying it on different material particles. So thus in some cases it behaves like a particle, while in some other cases so it behaves like a wave. Now the question it arises, how do these two different natures, they contradictory aspect or they have the connection, how they are being changing so at a same time. So the first attempt to explain this dual nature, so which can be changed anytime, so it was made by Schrodinger by treating each of these moving particle and particularly the electron. So he treat those moving particle as a wave packet. So you all are familiar with these wave packets. So what is the group velocity? What is the phase velocity? So I will not go in detail. So for these simple introduction, you can follow the quantum mechanics of graduation level books. So you will be get all these concept very much clearly explained in these reference books. So of quantum mechanics for graduation. So a wave packet it comprises a group of waves. So each with a slightly different velocity and wavelength with phases and amplitude such that they interfere constructively over only a small region of space. So where particle can be localized outside of which, so the particles they particularly can be localized in some sort of within those waves. So this is a big wave. So if I consider, so if there are small number of waves which can move, so this big wave which is moving, that velocity is known as the group velocity, and the particular different, so there can be number of waves which can moving along, and this whole packet that is generally known as the wave packet. So such a packet it moves with its own velocity, which is generally known as the group velocity, so which is equal to the velocity of this material particle. So thus a material particle when it is in the motion, it is equivalent to a group of waves, so that is a wave packet. So he derived this equation. So if a material particle it is considered as a wave packet, so it is necessary to explain the existence of a guiding wave. So he derived this Schrodinger equation. So he described this motion of this wave packet through this equation, that is del square psi plus 2m over h square E minus V into psi, which is equal to 0. So where E is the total energy, that is the total kinetic energy, V is the potential energy of this material particle, and the quantity psi that is generally considered as the wave function. Now if psi star, so that is the complex conjugate of this wave function psi, and when according to this Max Born approximation. So psi star, so that is generally considered as the psi square, which represents the probability of finding the particle. So in unit volume. So what does it mean? So it means that the probability density of the particle in the state psi. So probability of finding the particle, which represents the probability density of the particle. So within this wave packet, so which is having a wave function psi. So this function psi, it is sometimes called the probability amplitude for the position of this particle. So this Max Born hypothesis, it suggested and showed that the quantum mechanical laws and results of their measurement, so it can be interpreted on the basis of these probability consideration. And what is the basic physical significance of this Schrodinger wave equation? So it relies that the amplitude of the guiding wave to the probability of finding a material particle at a particular instant of point. So what does it mean? So it means that if the amplitude of the guiding wave is 0, so at a certain point in space, so what does it mean? It means that the probability of finding the material particle at this point is uh, infinitesimal. So that is very large. So if the amplitude is very small, so for example, if I have a very small amplitude wave, packet wave, so what does it means? It means that the particle which is acting as a wave nature at that particular instant of time, so the probability of occurrence of the particle, so it can be within anywhere within this wave packet, so that the probability of finding the particle is very large if the amplitude of this wave packet that is very small. Now as the value of this amplitude is small at all points except in the wave packets, so hence the probability of finding this material particle within this region of the particle, it is maximum. So if amplitude is small, so probability of finding the particle, so within this wave region, it is maximum. So thus it is possible to find an equivalent particle in the region of this packet, so which is traveling with this group velocity v. So in this we can say that the wave particle plus this guiding wave possess the properties of a particle which is moving with velocity v, and that wave packet, it is exhibiting the phenomena like interference and you can say diffraction, polarization of light. So thus the particle and wave properties of the matter, so they are strictly complementary. So this particle and wave nature, so they are complementary or complementing each other. And the link between these two concepts, it is being given by this Schrodinger wave equation. So this equation, so that is who explained through this de Broglie hypothesis. So classically, so if I relate the same idea classically, so classically a moving particle, it has some a definite momentum and it occupies a definite position in space. So it is impossible to determine both its position and momentum simultaneously, so with accuracy. So classically it is next to impossible, or it is not possible to determine the position and momentum of a particle simultaneously. Now as the time goes, as the quantum mechanics come, so in it has been apparent that the classical point of view represents an approximate which is adequate for the objects of appropriate size. So According to this quantum idea or this Born probability, the interpretation, the particle may be found anywhere within this wave packet. So this implies that the position of the particle is uncertain within the limits of this wave packet. So for a larger wave packet, so with the having many crest, the velocity spread is very small. So the particle velocity or momentum, it can be fairly accurately determined. So but the position of the particle, it is very uncertain. So what does it mean if I try to relate it with some other different idea? So for a small wave packet, so if I have a very small wave packet, the position of the particle, it can be more or less fixed. So as it is having less amplitude, so the position of this particle, it is almost fixed. And the velocity spread of such a particle is very large, and so the velocity or momentum of the particle become uncertain for this small wave packet. So quantum mechanically we can say that it is possible to determine, so according to quantum mechanics, so it is possible to determine simultaneously both the position and momentum of particle with accuracy. While in classical mechanics, it is impossible to determine this position and momentum of the particle simultaneously. Now, Heisenberg state a universal principle. So, what is this Heisenberg uncertainty principle? So, it says that the product of Heisenberg uncertainty principle, the product of uncertainties in determining the position and momentum of particle is approximately equal to this Planck's constant. So if the position, it has some finite position of the particle within this wave packet, then its velocity, it is very maximum. And if we limit this momentum of the particle, so that is for a very large wave packet, so in that case the position of the particle, it becomes so very large. So they are correlating each other. So the delta P and delta Q, so that is equal to this Planck's constant. So where delta Q, it is representing the uncertainty in determining the position, while delta P, it is uncertainty in determining the momentum of the particle. Now, according to this above Heisenberg uncertainty relation, so smaller is the value of delta Q. So smaller is the value of this delta Q, more exactly we can determining the position of the particle, or conversely, the larger the value of this delta P, less exactly we can determine the momentum of this particle, and vice versa. So this relation is very important, and it is generally known as Heisenberg uncertainty principle, and which shows that it is impossible to determine simultaneously both position and momentum of the particle accurately. So along with this position and momentum relation, so this relation, it has a direct consequence of this wave particle duality and Born statistical interpretation, and this relation, it holds for all these canonically conjugate physical quantities like position and momentum.
so which we have written delta p, delta q, and this also related with this delta e, delta t, and delta j, that is the angular momentum, which is in relation with the angle, that is delta theta. So this is valid everywhere. So delta E, delta T. So this relation we have validated in our derivation in the pair production phenomena. So what are next is the postulates of quantum mechanics. So there are four postulates of quantum mechanics, and which are very important. So on the basis of these four postulates, we will derive our classical ideal gas expression, the partition function equation, and all these three types of ensembles which are present within this system quantum mechanically. So postulate number one is, so in classical mechanics the state of a system, it is specified by specifying these generalized coordinates like q's and generalized momenta coordinates, which we generally explained with this p's at any instant t. Now in quantum mechanics the exact knowledge of this position and momentum coordinates at a given time t, it is impossible due to this uncertainty principle. Therefore in quantum mechanics the state of this system, it is completely determined by the state function, or which we generally known as the wave function psi, which is dependent upon this uh, position and momentum coordinates which are changing with respect to time. So the wave function which is explaining the states of the system at different times, so it has the following properties. So this wave function, it is generally complex, so it can have a symmetric wave function or antisymmetric wave function depending upon the nature of a particle, so which we are studying. So second is, it is a continuous single valued and finite function of q and t. So third properties is, if psi star, it is considered as the complex conjugate of psi, then psi into psi star which are present in this unit volume, so that is equal to psi square into delta tau, which is known as the probability density of the particle. So which is the probability density that the system will be found within this volume delta tau at time t. So fourth is, for a material particle in finite region, so for example the particle in a box example, so we consider this psi into psi star which is equal to 0. So what does it means? So that the position of finding the particle, so that is infinitesimally small. So what does it mean? It means that if we integrate these psi into psi star, so that is equal to 1. So that is generally known as the normalized wave function. So second postulate so of this quantum statistics, that is how we introduce these operators. So operator postulate. Now what is a operator? Now operator, it is defined as the entity which operating on a function. So operator is an entity which operating on a function and converts it into some other function. So if we have a operator P, so when it is applied to our wave function psi, and it convert our wave function into some other entity, that is phi. So where P is considered as the operator, psi is our wave function, and phi is our transformed function. Now the typical examples of operator, so it can be differentiation, so it can be integration. So the operator of this differentiation is delta over delta q, and differentiation of this operator of this integration is delta q respectively. And the second postulate of this quantum mechanics is that with every observable particle there is associated an operator which can operate on a state function. So this operator P, so under some considerations, under some quantum consideration, it must satisfy the following properties. So first property is it must be linear. So the operator must be linear. So what does it mean? So it means, man, if u and v are arbitrary operands, so operands is on which this operator is being applied, so that is known as operands. So if I apply this operator p on these u operands, so it can be pu plus p delta v. So where p is the eigenvalue of this operator small p. So for an arbitrary constant, if I apply this operator to a constant, so it can be remain as it is. So in quantum mechanics, we are mostly concerned with these linear operators. That is, we will generally apply these differentiations and integrations to our different functions. So the next postulate, so for postulate 2 is our operator, it must be Hermitian. So that is for arbitrary complex functions of u and v. So u star operator p v into delta tau, that is we can write it as pu star v star into delta 2. So postulate number 3 is the only possible values which a measurement of the observable whose operator is p, so it can yield the eigenvalues. So if I applying this operator to a wave function psi n, so it gives the eigenvalues of that function psi n into phi n. So where p is our operator, psi is our function, and lambda n, they are generally known as the eigenvalues. So this is our eigen function and this is eigenvalues. And this satisfy condition that psi n it must be single valued, and the integration psi n star psi n delta tau, it should be finite. So next postulate is So when a given system is in state function psi, the expectation values, so that is the lambda of these observable whose operator p, it is given as, so p is the expectation value of operator, so that is generally given as psi star p into psi into delta tau. So the time variation of this quantum mechanical state function psi, it is generally determined by this time independent Schrodinger wave equation. So the time independent Schrodinger wave equation, that is H, that is the Hamiltonian operator. So if I apply this Hamiltonian operator to our wave function psi kt, so it is generally written as I h bar curly psi over curly t. So here the value of this wave function, it can be given as psi, and the time function, so it is generally written as IEN over h, where the energy which is dependent upon this time. So here this Hamiltonian operator h, so that is h, and this h bar, so it is equal to h over 2 pi. So this is our Hamiltonian operator. So these are some of the notations or the postulates which we will generally use in order to drive the statistical distribution of this Bose-Einstein particles and FD statistical particles. So what is basically this quantum statistics of this identical particles? Now, by identical particles, we mean that electron which cannot be distinguished by any inherent properties. So, if I consider the classical mechanic particle, considering the molecules which are present at normal temperature and pressure, and if I consider that the molecular density, so that is equal to 10 is to power 25 mole per meter cube. So what does it mean? The volume available for each particle, so that is equal to 1 over molecular density, that is 10 is to power minus 25 meter cube, and molecular radius, so if I consider that is approximately the size of the atom, which is 10 is to power minus 10 meter. So from that we can calculate the molecular volume, that is 4 by 3 pi r cube, which is of the order of 10 is to power minus 30 meter cube. So that is of the this much approximate order. So as the molecule, it is much smaller than the volume available for it. So in principle, so identifying every molecule of the gas, so the molecules or the particle, they are distinguishable in classical particles. Now if I talk in this quantum mechanics, so a particle, it is generally described by a wave packet, so and it is following this Heisenberg uncertainty principle. So therefore there is no way of keeping track of these individual particles or molecules separately, and if they interact with each other to an approximate extent. Hence, in this quantum mechanics, the wave function of the particle, so they overlap considerably. So as a result, this quantum mechanical particle, so they cannot be distinguished. So as an example of a quantum particle, so considering the same electrons, so let us take the conduction of electrons in metals. So in that case, the density of electron, so that is approximate 10 is to power 28 per meter cube, and the volume available, So for each electron, that is of the order of 10 is to power minus 28 meter cube. And since for a energy of 1 electron volt energy, the momentum of the electron, so that is equal to 2 me under root, so that comes out to be equal to, so 2 into mass of electron 9.1 into 10 is to power minus 30, and energy of 1 electron volt, so that is 1.6 into 10 is to power minus 19 joule, so under root. And from that the Heisenberg uncertainty principle, I can find out the position of these electrons, that is h over delta p. And if I put the value of this delta p in this equation, from that I can find out the position of these molecules, that is of electrons in a metal. So that comes out to be equal to 1.3 into 10 is to power 9 minus 9 meter. Hence the volume, therefore the volume of this conduction electron, so that is equal to 4 by 3 pi r cube. So that is the particle, so delta q it is considered as r. So it comes out to be equal to 10 is to power minus 20 meter cube. So comparing this volume of a conduction electron to the volume available to it, so volume available is 10 is to power minus 28, and volume of conduction it is 10 is to power minus 27, so that is larger. So it means that electron wave function it overlaps considerably. So electron wave function it overlaps. So what does it means? That is the conduction of electron cannot be identified separately, and hence these electrons in quantum statistics they are considered as indistinguishable. So therefore two general categories of a particle we generally distinguish or define, that is for classical particles, so which are considered as distinguishable, and whose each energy we can calculate separately, because we can distinguish them, we can recognize them, while in quantum particles we generally consider the particle as indistinguishable. And in some cases when the quantum particle density it is sufficiently low so that their uncertainty is small in comparison to the volume available to them, so only in those cases the quantum statistics it obey these classical statistics. Otherwise for a very large number of particles the quantum statistics it show discrete energy or different energy notations. So in the case of quantum statistics, we can only distinguish between the states of the systems and not the different states of the single particle. So therefore in quantum statistics we generally consider the total energy, so En, so that is the summation of Ni into Ei. So here we have used this summation, while in classical statistics we use integration, because in classical statistics the energy value of the various cells so they are considered to be continuous, so while in quantum statistics the energy value of the various states of the system they are considered as discrete. So in classical statistics, the particle, what we do is we will find out the partition function of a single particle, and then we from that we generally derive the partition function of this nth particle, generally summation by considering the summation up to the order of n. So, but in quantum statistics, it is necessary to use this partition function for the system as a whole. So, in quantum statistics, use partition function for the system as a whole. So what does it mean? That means the partition function of the total system, so that is a summation of n with this prime summation exponential of minus of beta into en. So this prime on this summation, it indicates that we must not count those distributions separately which are obtained by interchanging of the two particles between two different quantum states. So why? Because the particle, they are considered to be indistinguishable, so which do not lead to a new distribution. So this is all about for today's lecture, and in our next lecture we will start the derivation using these energy and density operators, and we will derive or discuss these various type of ensembles with these quantum statistics. So if you have any doubt, you can write in the comment section, or you can ask me on WhatsApp. So, okay, dear students, see you in the next lecture. Till then, goodbye.